I was fitfully sleeping last night and just thinking, I'll just do this little thing. So it's kind of a little introduction to musical scales and all that. And we'll do more probably maybe next week. I want to do more. Maybe it'll come up next week. But anyway, we'll delay a little bit here. We hope to get the room started. Say hi to Shamash and Les and Benjamin in that order. Shamash, it's only you. No, I don't see your alter ego today. Just Logic Guy. Ah, I see. Yeah, we are shredding, baby. In fact, it's going to be pretty exciting. I'll give you a little preview of where we're going today. I have to like unmute this. I've got this. How's that sound? Well, so I kind of put that on purpose, but let's see. It just makes it sound better, right? Okay, I'm gonna turn it down a little more. There. Okay, so we're gonna be illustrating some things while I talk later on, and yeah, so that'll be kind of fun too. A new addition to the whole fun of the thing. Les, you came up quickly. You want to say a few words, or you? I assume you're hanging out, waiting for the fun to begin.
Oh, I just think the idea of having, you know, actual guitar available was great.
Yeah, it's going to be kind of important for some of the things we do. Benjamin's a guitarist too, and so yeah. Hey, Benjamin, how are you doing? Any news from the quantum entanglement front?
Good morning.
I
Well,
guess not.
I'm just thinking musical theory is gonna be the new hotness in physics because certainly string theory and quantum
Yeah, that's
theory
right.
have
This is a
gone
string
down
theory
in
bite of physics.
flames.
How about that? Yeah,
Yeah, yeah, you should have called it string theory.
I should have. I should have. What was I
Arranging
thinking?
is in
And we're
order.
joined by Corey. Corey, good to see you.
What's up, John?
Yeah, are you a musician, Corey?
Oh, absolutely. I play several. I'm mostly a woodwind player, but I do play guitar and piano as well.
Okay, well, good. Well, this will hopefully everybody will find some good stuff. In fact, I just want to right, and I do want to say I'll be talking about stuff that I know there are a lot of people that have some musical ability will probably take issue with some of the words I use, and we'll want to point out other things as well that go beyond what I talk about today, and that's absolutely fine. I do want to continue with a little more of the kind of the math and physics behind the diet or so the 12 tone scale in particular, kind of the Western the basis of Western music is what we're going to be looking at here. But yeah, if anybody has any anecdotes or a little historic, there's all sorts of fun historical things, terminology things. Feel free to break in and at any time and let me know that. It's good to have a woodwind player here. Woodwinds are based on vibrating columns of air, which have a very similar kind of harmonic structure to vibrating
Right.
strings, which is what I'm going to be looking at. So yeah, that's great. All right, so the link to the slides are up there at the top as usual, and you can open that up. It's a relatively small number of slides. We're going to take just a very brief peek at a few things really today. But even so, one of the things that was kind of intimidating to me putting this together is just knowing where to start. There's all sorts of really interesting, kind of interrelated mathematical concepts and physical concepts, and it's always hard to kind of know what path to weave through that. So I'm just going to kind of solve that problem by not taking a very long path through it today. Let me get VP up here on the stage. VP, You're invited. Yeah. So welcome to the stage, VP. And anybody else who wants to come up, anybody's welcome on stage as well. This may be a particularly good one to be on stage to ask questions or to chime in if you happen to be a musician yourself and know a few things about this. I will welcome comments. VP, are you
John,
mu-
if that was you, if that was you playing the guitar, it was coming coming in pretty clear. Are you using
I,
what you using? Man?
I just had, so I just this morning I got up. I was part of the reason I did this today was I was thinking, I'll bet I can do this. I had not I have a little mixer, a little Zoom mixer that I use,
Yeah,
kind
yeah,
of a
yeah, yeah.
podcaster thing,
Yep.
and so I have a Spark amp, and the amp has a headphone output, and I just took that headphone output, that stereo headphone output, jammed a monaural 1/8 inch plug into it, and just jammed that into a phone plug, into a an XLR. I have an
XLR.
XLR,
Yeah.
and just put it in, and it works. It just
Yeah, it
worked. I
works. It
thought it
works
would
really nice.
overdrive it or something.
No, no, no. It works. It works really clear. It's really nice. I like it.
Yeah,
Works good.
thank you. I love the setup. I don't know. I have in the past I've just mic'd my little Spark amp, but that just sucks because then it's got room ambience and it's got my podcasting mic kind of coming in through it. So it is a very cool setup. Thanks for noticing and commenting. VP, are you a musician?
No, no, but I'm just here so I can ask questions or comments whenever I hear something.
Uh-huh. Okay. Well, everybody's welcome. Get to anybody who'd like to. Welcome to come up on stage. Not going to be talking about controversial topics today, I don't think. So that's kind of fun too. Maybe we should get started. I'll try to get Andy up here on stage. Andy, did you come up? Maybe not. I don't know why he didn't automatically. I don't know why you didn't automatically show up on stage, frankly. But anyway, I'm inviting you up as well. There you are. Good to see you, Andy. Thanks for coming. Oh, and there's Shamash. There's Logic Guy's alter ego. Hey, Andy.
Good morning.
Good morning. All right. Well, let's go ahead and get started. Open up the slides, and we just go. Well, you see, this is Bitophysics number 97, coming up on 100. I'm kind of weakening on this. I must say, I really, as I said before, I was thinking maybe I wouldn't do one today, and then I thought, no, I can just do this simple thing. So here's what we're going to do today. We're going to talk about this. This is generally kind of a topic in psychoacoustics. And we're going to be talking. Psychoacoustics is the basis for the aesthetics of musical harmony. And in this, psychoacoustics is the study of the correlations between the physical characteristics of sound, frequency, and wavelength, and all of the things, acoustic reverberation off of echoing off of walls, etc., and what we perceptually make of all that. The perception, of course, is a psychological thing. The thing we are perceiving is a physical thing, and so psychoacoustics looks at the relation between those. And so elementary results are things like perceptual sound volume is correlated with, but not exactly the same as the pressure amplitude of acoustic waves. It depends on their frequency, depends on a lot of things. There's some perceptual things that can make acoustic waves with the same amplitude sound louder or softer, depending on how they're put together. And that pitch is correlated with frequency. The perception of musical pitch is correlated with frequency. Those are pretty simple things, but less elementary things include correlations that those correlations are, as I say, far from perfect. They're not exactly correlated. And one interesting area of psychoacoustic research that I was always interested in is how we localize sound using our binaural hearing. It's a remarkably complicated thing, and one day I may do another thing on that as well. As a guy who now wears hearing aids, I can attest to the fact that when you lose your high frequency hearing, working in noisy or trying to talk in noisy environments is really difficult, because if you have high frequency hearing, if you haven't lost it, your brain actually has an incredible ability to decide what to listen to. And if you don't have your higher frequency, you lose that ability because the brain uses the fact that the high frequency carries information about what direction to listen. You can actually directionally listen if you have high frequencies, and you lose that when you don't. That's really a fascinating thing, too. At any rate, today we're just going to look at the psychoacoustical basis of the 12-tone scale. Why is the 12-tone scale so ubiquitous, other than, of course, the fact that Western culture dominates? There are some good reasons for that. And even in non-Western cultures, 12-tone-ish things kind of show up for pretty good reasons. So, and as I say, feel free to chime in. I will pause from time to time, but I'll just go on now maybe to slide 3. So I'll start with the idea of overtones. This is a pretty simple thing. When we hit something like a bell in particular, and I'm thinking in particular of something kind of thuddy, not a string or not a column of air or something like that. We strike something, especially like a bell. That's a good thing, a good example of what I'm talking about. It vibrates for a while in a series of so-called resonant modes, and those resonant modes are determined by the mechanical structure of the thing. A bell has a bunch of frequencies that are almost random. Bells are constructed to have certain frequencies in their resonant structure, but they're not like a string. They're just kind of their frequencies at frequencies. They are resonant modes at frequencies that are not related in the way they are for strings and air columns. The lowest frequency of a thing like a bell is called its fundamental, and all the others are called overtones. When we pluck a string, however, or if we blow on a column of air with a woodwind or something like that, the overtone frequencies are very nearly integer multiples of the fundamental frequency. And in those cases, we call them harmonic overtones for reasons that we'll see here if you don't already know. The fundamental frequency of a stretched string is given by the wave speed on that string, v, the speed at which longitudinal waves move along the string, divided by twice the length of the string. And of course, the length you can measure easily enough. How do you find the speed? Well, the speed is determined by the tension in the string and how kind of thick and massive it is. As you probably can imagine, the tighter you draw up that string, the faster waves will travel along it. The more massive the string is, the slower waves will travel along it. And in fact, the speed is given by the square root of the ratio of the tension in the string to the mass per unit length. That Greek symbol mu stands for the mass per unit length. So on a guitar, the lower frequency strings are made that way primarily by making them have larger mass per unit length. They're thicker, they have more mass per unit length. That allows them to have pretty much the same tension as the other strings, but have slower wave speed, which leads to lower frequencies by the top thing there. So the overtones of a stretched string are given by basically an integer times v over 2l, where the integer can be any number from 1, 2, 3, 4, 5, 6, 7, etc. So let me stop there. That's kind of elementary stuff if you've gone through this before, but maybe some people haven't. And if there's any questions or comments, I welcome them. And once again, I would invite anybody on stage, especially musicians, if you'd, because you'll probably have things to say, etc. So, Corey, anybody else? Any comments on this?
Maybe.
Yeah.
Sorry.
Go ahead, Corey.
No, I was saying.
Not yet?
Can you hear me? I'm sorry.
Yeah, I can hear you.
Yeah. No. So I know with woodwinds instrument, anybody who plays a woodwind, overtones are really they really want you to practice overtones, because pretty much what you're doing is you're kind of training your ear and also training your embouchure to kind of hone in right at the the frequency that you need to play. So
Because you
you
kind
you
of
help
pick
develop.
out an
Hey,
overtone, right? You blow
absolutely.
hard
Yep.
enough to, yeah,
Yep.
right,
Absolutely. Yep. Yep. That's exactly right. Yeah.
right. And Shamash, I know you know some things about this too. A lot of people know things about this. Did you have a comment?
Yeah. I just wanted to see whether you're gonna dive deeper in this V over 2L thing, or should we just say one
I'm
word about
not.
it very quickly? Okay. So the actual reason for this is what you want is you want stability in your chord or in your woodwind or whatever. And for this to happen, you have to have an integer number of half wavelengths, if that makes sense. If it's any shorter, then the system will rearrange itself to play some other note that you're not desiring. Does that make sense?
Right. And I guess I should have. You're kind of referring to the middle figure on this page, which I didn't really say anything about. I'm going to be demonstrating that in a moment. That when you pluck a string, essentially what it does is it vibrates in what looks like a very complicated pattern, but one that you can literally mathematically construct by adding up vibration modes like those shown here, and those that have even shorter wavelengths than those shown here, going all the way up in, as most of us, or as a lot of us know, a thing called Fourier synthesis. You just add those different modes linearly, and you can construct any kind of vibration, any conceivable set of frequencies that you can get from those. And as you're saying, any frequency that doesn't produce a wave like this essentially self annihilates, because these are frequencies that when they bounce off of each end of the string just reinforce each other. Any other wavelength wouldn't do that. I think that was kind of what you were getting at.
Yeah, absolutely.
Let's see what it did bring to mind. One thing I wanted. Oh, I did want to just mention this. In two places on this slide, I talk about very nearly. I talk about the overtone frequencies being very nearly integer multiples of the fundamental frequency, and further down there, I talked about the speed being given very nearly by square root of tension over mass per unit length. And part of that, there's a lot of reasons for that, but part of the reason for that is that wave speed is partially determined by tension, but it's also partially determined by the stiffness of the string. Even if the string had no tension in it, if it were stiff, there would still be a wave speed along it. The stiffness itself can cause a wave speed. And
What do you mean stiffness? Like the actual type of material? If it's
right. Like you could just imagine basically a very large gauge wire, maybe 3 millimeters, have like a meter of 3 millimeter gauge steel wire. You could hold that at the bottom and have it stand straight up. It would be stiff enough that it wouldn't collapse under its own weight like a real string would,
I see, I see.
etc. So it's stiff, and because it's stiff, waves travel along it. Even if it's under no tension at all, waves will travel along it because of that stiffness. And in fact, what happens with a guitar string is that those the shorter wavelength modes, like the orange one at the top there, are affected more by the stiffness of the string, precisely because they involve more curvature. The more curvature you demand the string to have, the more its stiffness is going to be important. And so the higher frequency modes of vibration actually travel a little faster than the lower frequencies, and that leads to them not being perfect integer multiples of each other. So that's kind of an important. It becomes really important in piano tuning because of the fact that you have such an enormous range of stiffness and fundamental frequencies, and that leads to what's called stretch
I
tuning.
wanted
Go
to
ahead,
add, John,
Corey. Yeah.
too. I wanted to add too that similarly, especially for woodwind instruments, anybody playing instruments like saxophone or clarinet, whatever, you can tighten. If you the tighter your embouchure, of course, the higher the frequency, the quicker or the more the speed of the sound of frequency. If you loosen your embouchure, then you can also slow down the wave. So it's similar to you know,
Right.
the
It kind
speed
of
and yep,
it's kind of a stiffness thing, kind of your lip interacting, I
absolutely,
think, with the
absolutely, yeah,
reed, right, and pitching
absolutely,
it
yeah.
upward or
You're
downward.
right.
Yeah.
The speed of the read. Yep,
If you play the flute, you have to do it with your lips. So you tighten your lips
yep,
or you
exactly.
let your lips looser.
Yep, exactly.
And we got a couple more people. I think I saw Amit. Did I see you unmute for a moment? Thought I saw
Yeah,
somebody.
John, I
Yeah.
wanted to ask a follow-up question about what you were speaking.
Mm-hmm.
Is it possible that you are referring to the timber when you speak about the stiffness? Because that is one quality that comes into my mind that could be changing because of stiffness.
I missed the very first part. Say again.
I was saying, is it possible that it is the timbre of the sound that is
Oh,
changing?
oh yeah. Okay.
Timbre.
Timbre, I think, is the way we actually pronounce that, even though it's spelled
Yeah,
timber.
sorry.
Yeah.
We pronounce timber here, so yeah,
Yeah.
that's
Yeah,
if
so
that's okay.
timbre has to do with the how much of the various frequencies you have. Let me demonstrate timbre, maybe just with my guitar here for a moment. So like if I pluck a string, pluck the D string toward the middle, you get a sound like that. If I pluck it up near the bridge, it's the same pitch, but it's a very different quality timbre. That's an example of timbre, and the reason for that is that when I pluck it near the bridge, I'm exciting a lot more of the higher frequencies, which is why it sounds kind of, sharper than it does when I pluck it here. So that's an example of timbre.
And to add to that, when you're plucking near the bridge, we can say that the string is stiffer around the bridge and much more flexible near the center. And that is why the
Yeah,
timbre is differing.
yeah, well, that's not. It's not really so much that the string is just as stiff. It's just that when you pluck it, of course, near the bridge, the stiffness kind of becomes. It's not stiffness really, even there. It is harder to pull the string aside near one of its ends than it is at the middle. But that's once again really just because of the tension and the fact that it's really attached right there. So you can't really pull it aside much more. The stiffness is a thing that works all along the string and does raise the higher frequency overtones a little more than it does the lower ones. But that's not really about where. It does affect what you call the timbre in the sense that the frequencies now are not perfect integer multiples of each other, and that changes the quality of the sound. So there is that effect of the stiffness. Yeah,
Hey,
go
hey,
ahead,
John.
Sky. Yeah.
Hey, yeah, interesting topic. Yeah, I'm a musician. Yeah. Are you going to? I'm wondering if you're going to go into what's so-called just intonation.
That's next week probably.
Okay.
I'm gonna end by mentioning it today, and I do want to. That was the motivating thing for this. I intended first of all just to get right into that, but then I thought, nah, we'll kind of ease our way in. So we will get to that probably next week, and I will mention it before we finish today. Yeah.
Yeah, this
Cool.
this topic is really interesting to me. So and I'll stop comparing the guitar with the saxophone. I'll stop because I'm working at right now. But this is so interesting. That's why I'm actually taking off just kind of talk. But you mentioned the timbre. So for us, we have a couple things that work with controlling the timbre of the sax, right? So we have the hardness of the reed. So I don't know if you're familiar with
Mm-hmm.
the different hard shapes, the hardness of the reed. You can go from 1 to all the way to 5 or 6 or whatnot. Also, when I was learning the sax, we would always work on uh, changing the shape of the throat and the tongue position on the actual reed. That would also change the so you can have like like a nice low warm sound versus like a high, a high sound, high really light sound.
Yeah, it's interesting when we talk about. I don't play woodwinds. I've never really done that, but I played harmonica a little bit, and there's a little of the same thing, right? You end up shaping the note, kind of
Right.
drawing the thing up and down, and it's funny how with a woodwind, I think, or any kind of a wind instrument, and with the harmonica, it's all you almost feel sometimes like there's a direct from your brain to the instrument thing going on, right?
Absolutely.
It doesn't even feel like you're actually you're kind of doing what you have to do, but it's almost a direct mind meld with the instrument somehow. Very odd feeling.
Absolutely. That's true.
Yeah,
That's
yeah. Okay, well, let's move on to to the next slide here. So, if I can single out the overtones, that's what that diagram from the previous page was showing. For instance, with the guitar string, I can, oops, no, turn that on again. That's the low string, the low E string, plucking it like that. If I lightly place my finger at the midpoint, which is the 12th fret, I can force it to vibrate only in that second mode. So this is the black thing at the very bottom there. If I put my finger over the 12th fret, which is the midpoint, I get this. And you'll notice that those two sounds, I mean, if you're not if you are a musician, you know immediately what that is, but if you're not, you still might. Those two sounds, those two tones, pitches, have very similar character, but they're not the same. One's higher, right? When I put my finger over the 12th fret, it's a higher pitch. And those two pitches are related by the fact that the second one is exactly, or very close to, twice the frequency of the lower one. And that's called a musical octave. Now, there's no reason you should understand why would you call that an octave. We'll get to that eventually, but that interval is called an octave, and it represents a frequency ratio of 2 to 1. If I put my finger over the 7th fret, that divides the string into 3 and forces the string to vibrate only in that mode shown by the blue thing, and you get this. That's even a higher pitch yet, so I'll play all three of them. Boom, boom, boom. That sounds like that ought to be something. In fact, this is kind of, that's kind of the call of the Valkyries or something, right? Boom, da-dum, boom, ba-dum. That's a really classic interval called the musical fifth. And it's very recognizable. It's iconic. It's heraldic. All of those things. It calls to mind all those things. That's called a musical fifth. Why a fifth? We'll get to that. But there's a reason for that. If I go up, if I now divide it into 4, I get this note. So let's do all those again. There's the fundamental, the octave. Oh, sorry. I'm sorry. I didn't go up there. That's 4. Dividing it into 4, I get this. So here they are. Fundamental, octave, octave and a fifth. And that last one, dividing it into 4, is 2 octaves above the fundamental. I'll just play the fundamental, the octave, and the 2 octaves. And I think you can hear that those all have the same kind of musical quality, even though they're different pitches. The only one that's been different so far is that third one. I'll play the 3 octaves first. Oops, sorry. And now, that's the 5th. And that's the one that kind of stands out as different. Okay, without belaboring the point, let's just keep going up. That's 2 octaves. Now I'm going to go up. That's 2 octaves and a major third. Why a major third? Well, we'll get to that. And this is, if I go up to the next one, that's 2 octaves and a fifth. That sound is very similar to this sound. They're different by an octave. Sorry. And then I can go up higher yet. Ooh, there's a weird one. That turns out to be, oh, I said a dominant seventh. I meant to say a minor seventh there. I screwed that up. That's a minor seventh. Why a minor seventh? Well, we'll get to that too. And then if I go up even higher yet, I can get to 3 octaves, and I can go up. That's 3 octaves and a second. Why a second? Sometimes that's actually thought more of as a ninth. That's an octave and a second is a ninth. A lot of names here. I'm just telling you this. I'm going to go through the whole series so you can hear it. And you kind of hear all those. The nice thing about that, except for that weird minor seventh, listen to these, just these notes. Boom, 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 boom. Those turn out to be the notes of a major, of what's called a major triad. Just take those last three. Now I'm playing other strings. That's an E major triad musically. And it's composed from those three notes. E major triad. And I can play those all sorts of ways. Those are all inversions of an E major chord, which is composed just of those three notes in different octaves, different arrangements, etc. And they come directly out of this harmonic sequence that we get from the string. I say there's a lot of stuff there we have to get back to. Why are we calling them octaves, fifths, thirds, sevenths, ninths, seconds? Where's all that coming from? And we'll get to that. But I'll stop for a moment if anybody wants to make a comment or ask a question.
Yeah, I was going to say this sounds a lot like my musical theory.
Yeah. So at the beginning, I played a little theme, a little bit of from The Sound of Music, Do Re Mi, and then Woody Guthrie's Do Re Mi as a little trick at the end. But so you Do Re Mi Fa Sol La Ti Do is this. That's a major scale. We're going to get to that in a second. Do, re, mi, fa, sol, la, ti, do. That's an A major scale, as it turns out. And you can play things with... Ooh, there's a chord. There's a minor chord. But the whole Do Re Mi thing is really like based around this scale that we get from kind of starting with that harmonic series, and we're going to get into where that comes from now. So once again, I'll just stop for a second if there's any comments or questions. All right.
Hiro wanted to say something a minute ago. Yeah.
Oh, yeah. Sorry. Go ahead, Hiro.
Hey, so backing up just a little bit, when you did I'm driving right now, so I can't really watch anything. But when you did that, I think you called it the major triad. That was all on the low E string.
The harmonics were so this.
Yeah. And was that what? So what frets are those?
So that's the 7th fret, the 5th fret, and then approximately the 4th fret, but not exactly.
Okay.
Yeah.
Thanks.
Let's see. What was I? I thought we were going somewhere else with that, maybe. But anyway.
Oh, wait, you're going off fret to get those harmonics.
Yeah, you definitely have to go. So, for instance, there's the fifth fret. This is a little bit below the fourth fret. This is a little bit above the third fret. This is right in between the second and the third. That's that minor seventh. And then the 3-octave one is just above the second fret. But you can just play with it, right? Just put your thumb places until... If I put my thumb in a bad place, I get stuff like that. So it's only when you put your thumb or your finger at the right place that you'll get a nice pure tone. And it helps
So
to pluck near the bridge.
Why
Yeah,
isn't it right on the fret then?
Because the guitar is not actually tuned in what's called just intonation. You know, we've got what's called what's the word for it?
Yeah, it's equal temperament, but that's not
Equal
actually the
temperament, yeah.
reason.
Equal?
It's
Really?
Yeah, it's not
It has
actually
to
the
do with our
reason.
perception, right? Because our ears distort the actual sound as we hear it.
Yeah,
So you
well,
got to go a little bit higher in reality to hear it right.
it's complicated because, of course, what I'm doing is I'm taking the length of the string and I'm making it half, 1/3, 1/4, 1/5, 1/6, 1/7, and 1/8. Sorry, 1/8 right there. But 1/8 of the string is just in no way anything like where you would want the second fret to be. The second fret is determined by a different kind of mathematics in whatever kind of a scale you use. So you would never put it at the eighth way point like that. Things work
Because
pretty
of equal
well.
temperament. Yeah, because
Sorry?
of equal temperament. Because of
No.
equal temperament, surely.
It's actually not. I know what you're saying, but it's actually not that. This thing is not because of equal temperament. The difference between just and equal and Pythagorean we'll talk about probably next week. But this particular thing actually isn't. There's no scale in which you would want a major second, essentially, is what that interval is, the second fret, a major second, or a second, I guess I should say. There's no scale in which you'd want that to be, 1/8 of the way up the string. You would never put the fret there for any kind of tuning. So it's a little more complicated. It has to do with the fact that the first few things, right, the first harmonic is really exactly at the 12th fret. The second one is exactly at the 7th fret. The next one is exactly at the 5th fret, but then it's just not anymore. and it's just because of the way those things divide up. Okay, let's see. So I think let's see, what did we do? Oh, yeah, okay. So that was singling out the overtones there and all those weird names. Let's go back and let's just talk about for a moment the major diatonic scale, especially in relation to a piano. The nice thing about a piano is they're just laid out there. You can see them. If you know anything about the piano, you might know how to find an A or a C, and from there everything else follows. The white notes, if you play the white notes upward in sequence, starting at any C on the piano, you get something that sounds like this. Right, do, re, mi, fa, sol, la, ti, do. Right, so it's just the do, re, mi thing. And let's see, what did I want to say about that? Yeah, well, anyway, so it is the most familiar. And so let's start right now. So this is the 1 of that scale. This is the 2 of that scale. This is the 3 of that scale, the 4, the 5, the 6, the 7, and the 8th one is the same as the first one. So that's the 8th note of the major diatonic scale. They're an octave apart. Why is it an octave? Because it's 8 notes. 1, 2, 3, 4, 5, 6, 7, 8. Now, interestingly enough, the intervals between those aren't the same. The C and the D have a black note in between them. The D and the E have a black note in between them. But the E and the F don't. and so on, right? The B and the C don't either. They're called half steps as opposed to the whole steps from C to D, from D to E, the notes that have black keys in between them. And the idea with equal temperament, as Sky was referring to before, well, temperament in general has to do with how we decide specifically to assign pitches to those keys. Sky, did you want to talk a little bit about that? I mean, I think you know something about it. You want to mention something about the equal just difference here? I don't know if this is a good place for that or not.
Okay, yeah. Well, my understanding, I mean, what we call the equal tempered scale was only invented, was it 250 years ago? I mean, in the time
around
of
the
Bach.
time of Bach, right?
Yeah, because before that, if you built a keyboard, you could only play it in I think 2 keys because of this difference between the actual harmonic intervals.
Right.
And as John was saying, the octave is a definite, on the 12th fret on the guitar, it's exactly halfway on the string. So if you want to be able to play in various different keys on one keyboard, they instead of being in perfect, what's called just intonation, where the mathematical vibrational ratios between between the different notes, there's like a compromise. In order to be able to play in all the different keys, starting from different root notes, all of the notes on the tempered keyboard are slightly adjusted, and we've just become so used to that for the past 200 odd years in Western music that when we hear music that's made in so-called just intonation, it sounds a bit off to our ears because we're so used to the tempered scale.
Yeah, it is really interesting, and this is something I definitely will spend basically the whole time next time probably talking about. Is essentially, if you want to look ahead to the last slide, you'll see the thing that I want to compare just, equal, and Pythagorean scales, which are kind of primarily really nice. If you understand the difference between those, you really kind of see the kind of compromises that we make. What you really want to have is for all of these overtones. This is the thing that Andy called my attention to. Andy, you're driving, but I don't have that link. I should have put that link in here. Andy called my attention to a really nice video, I think on, what was the channel? Is it that blue? No, it's not the blue black. It's Minute Physics, I think. Oh, maybe Andy's.
Yeah, no, I think it was Minute Physics. There's the one about the dissonances, the math.
Yeah, dissonances, right.
What did I say that wrong?
Dissonance? Yeah, and it talks about how you want the overtones to line up. And it's really the fact that you want the overtones to line up, not just that you want fundamental frequencies to have nice integer relationships. Anyway, those of you that know something about that, it's a great video. Maybe later on I will look it up, or maybe Andy will be out of his car and he can put it in the chat or something. Sorry, I'm getting way ahead of myself here. So you can build major diatonic scales starting with any of the chromatic pitches. On a piano, the frequency ratio between any 2 adjacent notes is supposed to be something like, catch this, the 12th root of 2. So the frequency ratio between a C sharp and a C is intended to be the 12th root of 2. And then from C sharp to D, the 12th root of 2, from D to D sharp, I should say, the 12th root of 2, from D sharp to E, the 12th root of 2, etc., so that you do that 12 times, and the 12th root of 2 times the 12th root of 2 times the 12th root of 2 12 times gives you 2, and you end up an octave higher at the end. This is the idea of equal temperament, is that the frequency interval between every 2 adjacent chromatic notes is exactly the same, so that you can play tunes in any key you want. If you know how to use black notes, I never learned how to use black notes, so I always have to play in the key of C. But if you know how to use black notes, I can do that on the guitar, but not on the piano. You're in good shape. And you can then construct diatonic scales the same way. Notice that the first interval in a diatonic scale is a whole step. It goes 2 half steps from C to D, then 2 half steps from D to E, and then a half step from E to F. Here we go. C, whole step, half step, half step. Now from F to G, whole step, G to A, whole step, A to B, whole step, and B to C, that's a half step again. It's hard if you don't have a really good musical ear, you won't notice the difference. But those 2 half step intervals are half the size of all the other intervals in that note. It just sounds so normal to us that we rarely even notice that.
Maybe you can play a chromatic and then a major
Yeah.
after.
So I was just about to do that. Thank you for mentioning. So I'll play a chromatic scale starting at a C. That was 12 half steps, playing all the black notes and the white notes. And you see, it's not very interesting, right? Oh, sorry, I missed one. It's just a bunch of half steps. But in there, of course, there's the diatonic scale. And I should mention, at this point, too, let's see, is this where I want to do it? Okay, no, we'll do that in a moment. I will maybe mention just right now, why C? Why does it start with C? Why isn't that A? Why isn't that C and A? And I learned recently, I think this is a true story. Somebody can correct me if I'm wrong. But as I understand it, the reason the C is the start, it has to do with the fact that back in the old days, most music, back in the Gregorian monk days, they were a sad lot, and they did most of their music in a minor scale, specifically this scale. That's an A minor scale, as we call it, and you get it by starting on the A and just going on the white notes. A, B, C, D, E, F, G, A. Etc. And apparently that's why it's A. But at some point we became happy. And we started not starting on the A, we started on the C. Isn't that happy? So much happier when you do that. As opposed to... Anyway, that's kind of a fun little piece of history.
I'm not sure about the sad monks bit, but what I do know is that the first key on a piano is an A. So that's the lowest note.
Oh, is it?
Yeah. So if you go right to the left of a big piano, a grand piano, the first note is an A0. So what we call A0 today, right? And so that you have to start with A, because this A, B, C, D thing is a later development on the do, re, mi, fa thing. So
It might be. I don't know. So you're suggesting that the whole labeling of the notes, what came after the piano was created. The
ABC thing is much more modern than the invention of everything else.
Maybe. I guess I'm a little skeptical that we didn't label the notes that way before we had pianos, but you might be right. This is my fractured history, maybe your fractured history, maybe we're both wrong, who knows. But I will, at least at the moment, concede I don't really know. But I really like that explanation, because it is the case that Gregorian chants tend to have that minor kind of tone. Whether they were sad or not, I don't know. Okay, so let's move on to 6 then, and to slide 6. So why those names? Now we kind of get it, right? The whole going up. That's an octave because that's 8 notes up the scale. 1, 2, 3, 4, 5, 6, 7, 8. It's the octave. So that's what you get. Why a fifth? Why an octave and a fifth? Because if I start at the octave, 1, 2, 3, 4, 5. 1, 5, 1, 5. That's a fifth because it's the fifth note of that diatonic scale. Then we get the 2 octaves. Then we get the major third. What's the Why is it a major third? Well, first of all, here's the scale, the diatonic scale. That's the third note. 1, 2, 3. As opposed to a minor scale. 1, 2, 3. 1, 2, 3. 1, 2. Oh, sorry. 1, 2, 3. That's minor. 1, 2, 3. 1, 2, 3. 1, 2, 3. So the difference between that first and second one. Sorry, Corey. What did you say?
The flat third.
Yeah, the flat third, as it's called,
Yep.
right? A major scale has. Go look at the C to E. E is the third note. It's 2 whole steps up, but in the minor scale, we go from the C to the D to the E flat. So it's a minor third there. We're talking about a major third here, 2 octaves in a major third. Listen to that interval again. Oh, sorry, there's the octave, 2 octaves. Here's the next one. 2 octaves to the next one. It's a major third. 1, 2, 3. So that's why it's a third. And then 2 octaves and a fifth. We've already seen the fifths. We don't really have to hear that again. But notice that weird 7 one, a minor seventh. Now, what would that mean? If I start at the C, I go 1, 2, D. So 1, 2, 3, 4, 5, 6, 7. 7 is the B. A minor seventh would be a half step down. 1, 2, 3, 4, 5, 6, 7. Minor 7. That's the B flat. Minor 7. And now listen to what that sounds like harmonically. Oh, sorry, I started in the wrong place. I should have been... I should be doing it in E, so let me do that. 1, 2, 3, 4, 5, 6, 7, 7, minor 7, minor 7. And so, minor 7, as opposed to, major 7. Anyway, that's why it's called a minor 7, because it's that flatted B essentially of the C major scale. And then we get to 3 octaves. Then we get to 3 octaves in a second. I'm going to see if I can get this here. There's 3 octaves. Here's the second. Oh, sorry. There it is. Boom, 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 boom. There's E. Here's a D. It's the second note of the scale. But seconds are weird in music, and usually when you have a second in a chord, you play it with other notes. It doesn't function as a second, usually. Sometimes it can, and it's called suspensions. But usually when you have that second there, it's playing the role of what's called a ninth. It's really 9 notes up from the important note. And so if I start with an E and I add a major third, a common chord is then to add a 7 and a 9. 7 and 9, which is one step up from the... There's the 9. Put those together, you get this really nice jazzy chord called a major ninth. It has the 7, has the major, has the root, the third, a minor 7 and a 9. And then I could put another octave on top there. Okay, sorry, way too much terminology, but that's at least why those things are given the names they are. Let me get back to my computer just down on me. There. Okay. All right. So sorry. Let me stop for a second. See if there's any comments or questions.
I just Googled the ABCD thing, and you would not believe how recent it is. Every
Really?
reference I'm finding says it's 1980s
Oh, well,
by
that's not
someone
true.
called. Yeah, okay, well.
That's an AI hallucination.
No, it's not AI. I'm reading the Wikipedia pages. So it's apparently something called someone called Chris Walswall or something like that, and he developed it because they wanted to write computer music, and it made things a lot easier to notate it like that. Especially that he wanted to write down folk music, which wasn't written in classic, notation with
Well,
Groschens or whatever.
I guess I'm not sure what you're. I mean, surely you're not saying that the names of the notes were created in 1980. They've been around a lot longer than that.
I know for a fact that the ABC thing is much more recent. I'm telling you, and everybody used to learn music in do re mi fa, and this goes way back to the monks. So this is someone called Gio d'Arezzo in Italy who came up with it because it's a text in John, and so we can tell that story. But I know that that's way older than saying ABC.
Well, sorry, what do you mean the ABC thing? Sorry, what do you mean?
Calling notes ABCD using the first 7 letters of the alphabet instead of.
I mean, that's been true since well before Beethoven and Bach, right? And Beethoven wrote symphonies in C minor, etc. Right? So
he
goes back hundreds.
He actually wrote the word C minor.
Yeah, I think. I mean, I could be wrong. Oh yeah, no, I mean
it's from Latin.
Yeah. Go ahead, Kathy. What do you know?
Yeah, it's from Latin translations from early Greek music transcripts, and my guess it would just be because the C. I don't know what the right terminology is, but it kind of it fits with all the scales of the notes.
Bach's harpsichord music, I think, is such and such in C sharp minor, or whatever. So I mean, even before the piano, people were talking about that. I think the harpsichord was laid out like a piano, and I think had the same letter names. I could be wrong about that, but I don't think I am.
I don't believe you. I'm actually willing to put money on this.
Okay, well.
No. So Beethoven never said C minor. There's no way.
Wow. Okay, that's going out on a pretty big limb, Shamash. I don't know. We'll have to see. Okay, I'm willing to be corrected, but I'm going to be shocked beyond belief if that's true.
I was a musician before the 1980s.
Yeah, I certainly was too. Yeah. I know it dates back to the 1950s, and I would have guessed it went back to at least World War II. Just kidding. I mean, it's further than that. All right. Well, so there's that. That's 6. Let's go on to 7, other scales. So I already talked about the fact that if you play the white notes on the piano, starting at A rather than C, you get this minor scale. In fact, you get what's called the natural minor scale. But if you sharp the 7th note, the G, the 7th note in the A in the scale beginning with A, you get what's called the harmonic minor scale. Let's just listen to the difference in feel. Here's the natural minor. If I sharp that 7th note, you get that, which is called the harmonic minor scale. And I wonder if anybody, that conjures in my mind a real feel that I could label, I think. I wonder if anybody has a sense of what that conjures up in their brain.
Quentin Tarantino.
Quentin Tarantino. Oh, that's nice. And I think you're right, Kathy. I wasn't going to say Quentin Tarantino, but I was going to say surf music. Is that what you're thinking too?
More like the with the Hispanic influence.
Yeah, that's right too. That's right. Surf music and a lot of Quentin Tarantino stuff like that has that kind of. It's kind of like there's something exotic, Spanish, sometimes Middle Eastern. A lot of surf music has Middle Eastern kind of influences, and I think that it starts to conjure that up for me. That interval is weird. What makes that interval weird? Look at what I'm doing. I'm sharping the G. That means I'm going from F, if you look at that keyboard, I'm going from F all the way up to G sharp. That's 3 half steps. That's what makes that interval so kind of stand out. And so, and it has a very different feel from the natural minor. And if you sharp the last 2, you get this. Oh, so. It's kind of like a combination between minor. There's the minor. At the end, it's kind of majorish. It's high, right? They're sharp. Both of those notes are sharped. But now you're back to a situation in which you have only half steps and whole steps. Once you sharp the F as well as the G, now you're going from E to F sharp. That's a whole step. F sharp to G sharp. That's a whole step. So you eliminate that weird 3 half step interval. And it can get weirder yet. I mean, for instance, listen. Oh, sorry. Oh, sorry. That's very, to my ear, very Middle Eastern or something. Shamash, does that yeah, you're the expert there. Does that sound?
we use that scale all the time. It's they say it's something like Saudi Arabian or whatever, but that's not true. And the only reason people are marrying it to that region is because every Hollywood music would put that music whenever they have a camel and some sand.
Right.
I just wanted to say a quick thing about that seventh when you sharpen it. So when you have a last half step in the minor scale, we call this the sensitive note actually in Arabic music, and they make a huge deal about never ending on the sensitive because it's so annoying for someone listening. It leaves them waiting for that final relief, and if you don't know what you're doing, you're gonna destroy that. It's very teasing.
Yeah, I love ending songs with something like if you're doing this, you go. End on. And that's a 6th, actually, that I'm ending on there, but doing something very out of the ordinary. Very odd place to end. Let's see, where were we on that? So I think that here's the scale that I just played at the end there is whole step, half step, 3 half steps, half step, 3 half steps, half step. That's what makes that scale so odd.
Yeah, we call this Nikriz.
You call it what?
We call it Nikriz scale.
That particular one.
Yeah.
Okay, well, I'm not going to call it that. I don't even know how to say it.
Screw you.
Oh, damn, I lost my computer again. Hold on a sec. It keeps timing out. I'm playing too much stuff here. All right, so that's all that. We're almost done here, I think. I was just going to maybe end with one more thing. Pentatonic scales. The scales don't have to have 7 notes, 8th notes if you want to include both octaves. They can have fewer notes, and really classic kind of thing in blues and rock are pentatonic scales. Like you'll hear things like this. 5 notes, 1, 2. that second one is a minor third there, and then a fourth, and then a fifth, and then a minor seventh, and an octave. Right? You don't have to use many notes to play something that starts, starts sounding a little less do re mi. So that's an example of a pentatonic scale, and there's lots of ways of choosing pentatonic scales depending on the feel you're looking for as well. So I'm pretty much done. I just want to give you a little preview of where we're going. What I want to talk about next week is this whole business of equal temperament, just temperament, and Pythagorean temperament. The Pythagorean is a nice way to start. What we do with Pythagorean is we start with a note like E, go up a major fifth. Remember, you can always recognize a major fifth because it has that bum ba dum kind of sound. That's going up by a major fifth. Here's another one. Bum 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 bum. Bum, bum, bum. You keep going up by major fifths, but then as you do that, every time you go up more than an octave, come back down. So I'll go, there's up a fifth, now I'll go up another fifth. But now I'm up more than an octave, so I bring this note down back into the original octave where it becomes the second. And now I go up a fifth again, and then I go up a fifth again, and then I bring that note down by an octave. Now I'm at that's the third, that's the major third, and now I go up by a fifth again, and I go up by a fifth again, and I bring that one down by an octave back into the original octave. And at this point, that's actually what's called an augmented fourth or a diminished fifth or something, however you want to call it. It's an interval of 6 half steps. It's sometimes called the devil's interval. That's a weird interval. It's a very ominous sound to it. And you just keep doing this. So we're going to talk about next time how you can kind of, by doing that, you can generate something like, but not exactly right, a diatonic, a chromatic 12-tone scale. And then if you tweak that Pythagorean into some better intervals, you get the just tuning of the first column in this diagram. And then if you kind of straighten those out so that the intervals are all exactly the same, which ends up making compromises that are unfortunate, but that gives you the ability to transpose tunes, you get into your equal temperament there. And all of those scales are shown with what are called cents. How many, those are actually the ratio of one frequency to another in terms of how many 1200th roots of 2. In the just interval, the ratio from the C to the C sharp, that 16/15ths, turns out to be 2 to the 111.73 1200ths. The sense is the sense is what you get from talking about how many 1200th roots of 2 you have between the two frequencies. And you'll notice that the equal temperament makes every interval 100 cents. They're exactly the same logarithmic. It turns out that's a way of doing logarithms. It's a 100 cents between every half step, whereas that's not true in Pythagorean. It's not true in just. Both of them have their nice features, but both of those have the problem that you can't play a tune in any key and expect it to sound like anything other than shit. So we make those adjustments. Anyway, I'm going to stop. We'll talk more about that next time. I'm going to stop there. We can share music stories or do whatever. Go ahead, Sky.
I'm remembering how my mum used to ask me when when I was first becoming a musician. She would say, "But if there's only 8 notes, how can they keep coming up with new songs, new melodies?"
Yeah, well, and a lot of legal cases, right? Plagiarism cases are based on juries that don't really understand the answer to that question. Um, a prosecutor, or what do I would say, a prosecuting attorney, what do you call them? I guess the plaintiff's attorney will point out, look, this note and this note and this note are the same notes in the same sequence, and they plagiarize my client. But of course, they might not be in the same rhythmic signature. They might. They might not come to the same place in a measure. There's all sorts of ways to shake things up, but that's definitely
Yeah,
definitely a
and at the
thing.
time, I said to her, "Well, no, there's 12 notes, not 8." That was
Yeah,
my
for one, Schoenberg. Schoenberg is famous for composing 12-tone pieces that played all 12 tones before repeating one. That sounded like you'd kind of expect it to, etc. Okay, so let's see. Anything else? So one thing I wanted to mention. Here's a thing. Here's a good thing to talk about. If you take nothing else away from this, you might take this away. Just listen to this for a minute. That's a really common thing, right? You hear variations of that all over the place. And listen to what's going on. Usually a musician would call this the one, the root chord, the one. And then we're going to the 4 chord. Why is it the 4 chord? Because that chord, 1, 2, 3, 4. 1, 4, 3, 2, 1. 2, 3, 4, 5, 4, 4, 3, 2, 1. The 1, 4, and 5 chords, if you know just those 3 chords based on a 1 of the diatonic scale, the 4 of the diatonic scale, and the 5 of the diatonic scale, you can play 90% of popular music because they just don't have anything else in them. And you can play 100% of blues because blues never has anything. I'm kidding, but pretty much never has anything else. And so you'll see musicians, if they're playing songs that they've never heard before, but they're jamming with somebody, the person that's playing it will typically say, "Well, okay, I'm not going to pick a song that's too hard. I'm going to pick a song where the musicians will probably be able to anticipate what chord I'm going to, and all I need to do is hold up 4 fingers or 5 fingers and tell everybody else on the stage I'm going to the 4 chord or the 5 chord. Occasionally, you go to the 2 chord." So 1, 2, 5, 4, 3, 2, 1. All just based on the root of those chords, what the note basically that the bass player would be playing. Etc. Okay, well, this has been kind of fun. As I mentioned earlier, I got up this morning and figured a nice way to patch my amplifier right into my mixer, and that makes this a lot easier to do too. I hope that's worked out well. Any other comments?
Maybe a couple of comments quickly. Mentioning the pentatonic scale, I think, and I've heard a lot of music, but I do believe that every music around the world has these notes, like these intervals, I mean. And
Yeah,
there's a
probably.
theory. Yeah, there's a theory around that, which is the ear vibration doesn't like when two notes are very close to each other. So if you play two notes that are very close, your eardrum has to vibrate in a very like non-balanced manner. I know I sound like a magical guy, but I don't really know how to explain this. So if two notes are hitting in the same at the same time or at equal interval times, something like that, yeah, that's very annoying to the ear. And so the pentatonic doesn't have that, and people have assumed that this is why we like octaves and we like fifths, because the airwaves are hitting our eardrums at very specific times, where if it's an octave, then it's 1 out of 2 times they always agree, so it's 2 hits and then the other one is 1, so they never mismatch. The major fifth is like 3 for 2, so every 6 times you're guaranteed a match, etc. So that's the theory behind it, or at least
Yeah,
that's the
there's
guess.
so it's a little different when you're playing scales or playing, solo lead lines than when you're playing chords and kind of trying to put notes together. As I was illustrating, like you're saying, you'd never want to put these two. Well, rarely would you want to put these two notes together. Those are half step apart. It's a very weird thing. Strangely, train horn. If you listen to a train horn, my band plays every month about 20 feet away from a Metrolink stop, and the trains come in and honk their horns. Honk? Do trains honk their horns? Anyway, blow their horns as they're coming by an intersection, and
They
it
blow
sounds
their
like
whistles.
this. It sounds like this. That's a classic train. Whenever train have two pitches, it's always that interval I talked about before, the augmented fourth. 1, 2, 3, 4, augmented. You play those together because it gets people's attention. That's a really attention-getting sound that says train coming. And that's always what you get. And if you put it with a little volume swell, you get the kind of effect of one of those things coming at you. But for instance, in blues, you'll have things. Bending a note to get not even a half step, right? It's important that you just get that character of slightly up, not all the way up. So pitches in lead lines have a lot more leeway because they're not usually sounding with some other note, unless you're going. So, okay, I think I'm done. Any other comments or questions? We'll play our way out here eventually.
Very quickly, is the first chord in A Hard Day's Night by the Beatles? What is the hell is that?
Oh man, books have been written on that chord, Les, and I can't remember. There's a great video. Somebody saying, "I figured it out." And it's everybody has their own version of it. I can't remember now. I worked out what I thought was the best version you can get on a guitar without retuning, and that's pretty pathetic. If you just play one guitar without retuning, you just don't really get anywhere near it. But as I say, books have been written on that chord. All right. Well, I kind of see people. I see guys like Alfonso down there. He's a budding musician as well. Lots of people who haven't had much to say today. Maybe you'll have more to say next week. Going going once, twice, three times.
Okay,
I'll
so
wait a few
to
more minutes
correct the
here.
misconception, it appears that there's a rich story that is connected to monks behind the ABCD. And I don't know a lot for now because I'm just Googling it. But it appears that the letter D stood for Dorian and the letter A stood for something else. And so it wasn't, there was no writing system, but these letters were denoting church modes. So people would remember
Right.
those melodies and give them names. They did not have a writing system. So maybe it originated there.
I think that makes sense because I think long before the specific pitch that we call A today was called A, there would have been the minor mode that you get when you start on the A of a piano and go up. So, it's probably some kind of a transition like that. I don't know what the mode would be called. I don't, is there a mode that starts with A?
Well, it's the A minor. If you just play
But I
white
mean,
notes with
but
A.
like Dorian, like you said, I'm not sure there is a formally named mode that begins with an A. I could be wrong. I could easily be wrong because I can hardly remember. There's
I don't know, but
Phrygian
I
and
just yeah,
Hypophrygian and all these things. I mean,
I don't know.
yeah. Well, at any rate,
But it's certainly something I'm gonna be looking into. So probably next week we'll have our answer.
bring your hat with you, Shamash. That's all I want to say.
Bring my what? Sorry.
Bring your hat with you. I want you to have something
What's
to eat. I want you to have something to eat.
I don't know that
Oh,
reference.
in at least in English, we talk about have someone eating their hat.
So what when
Have you
they're
ever heard
wrong
that?
is like that's what it is.
Yeah, you have to eat your
Okay,
hat. Yeah.
okay. Okay. I get it. Very funny, John. Yeah.
Okay. All right. So I think we will shut this thing down. Maybe there'll be an after party.
Maybe you can play instead of having the music play.
Yeah, right. Oh, I could. Oh, that's a good idea. Why don't I? Oh, I'll tell you, that's a good idea. Yeah, I think I'm even warmed up enough now that I could maybe even just play a little tune. I'll just do that. Whoops. My bad.
Free bird.
Yeah. Oh, what happened? Check. Okay, there's that. Why am I? Oh, I see it because I've got it muted. All right, so here we go. Oh, it's a. If you ever change your mind about leaving me behind, oh, bring it to me. Bring your sweet loving. Bring it on home to me. I know I laughed when you left, but now I know only hurt myself. Oh, bring it to me. Bring your sweet loving. Bring it on home to me. All right, take it away, John. told me you didn't need me anymore. Oh, it gets a little high for me. Well, you know, I nearly fell down and died. I guess you cried when you told me you didn't need me anymore. Well, you know, I nearly fell down and died. If you ever change your mind about leaving me behind, oh, bring it to me. Bring your sweet loving. Bring it on home to me. All right, there you go. All right, thanks everybody. See you next week.